Today, we're tackling a problem that challenges us to find the smallest starting value for a sequence of numbers, such that our running sum never drops below 1. It sounds simple, but there's a neat optimization waiting to be discovered. Given an array of integers, you need to find the minimum positive starting value. When you iterate through the array, adding each number to your current sum, this sum must always remain greater than or equal to 1. The goal is to return that smallest possible positive start value. A straightforward but inefficient approach is to try every possible positive starting value, beginning from 1. For each potential start value, we iterate through the entire array, calculating the running sum. If the sum ever falls below 1, that starting value is invalid, and we move to the next. We continue this process until we find a starting value that keeps the sum positive throughout. This method recalculates the sum for each candidate, leading to a time complexity of O n multiplied by m, where m is the answer and big O of 1 constant time space. The key insight here is that we only care about the lowest point our running sum reaches. If we ensure that this minimum running sum, plus our starting value, is at least 1, then all other sums will also be valid. So, instead of testing start values, we can calculate the running sum of the array elements directly, tracking the minimum value this sum ever achieves. Let's call this minimum running sum min_prefix. If min_prefix is positive or 0, we only need a starting value of 1. If min_prefix is negative, say -5, we need a start value of at least 6 to bring that -5 up to 1. Therefore, the required starting value is 1 minus min_prefix. We take the maximum of this value and 1, ensuring our start value is always positive. Let's trace this with the example, -3 2 -3 4 2. We initialize sum to 0 and min_prefix to 0. First, add -3, sum becomes -3. This is less than min_prefix, so min_prefix becomes -3. Next, add 2, sum is -1. Still less than min_prefix, so min_prefix remains -3. Add -3, sum is -4. This is less than min_prefix, so min_prefix updates to -4. Add 4, sum is 0, not less than min_prefix. Finally, add 2, sum is 2, again not less than min_prefix. After processing all numbers, min_prefix is -4. Our required starting value is the maximum of 1 and 1 minus -4, which is 1 minus -4 or 5. The maximum of 1 and 5 is 5. So the minimum positive starting value is 5. This ensures that even when our running sum hits its lowest point of -4, adding 5 brings it to 1, satisfying the condition. You'll spot this pattern when a problem asks for a minimum or maximum value that affects a cumulative sum or product, especially when the constraint involves keeping that cumulative value above or below a certain threshold. Think prefix sum or running minimum maximum to optimize. This optimal approach achieves a time complexity of big O of n because we iterate through the array only once. The space complexity is big O of 1, constant time, as we only use a few constant variables. This prefix sum technique is fundamental. Try the next problem involving running sums, same pattern. If you found this helpful, please like and subscribe for more efficient DSA solutions.